My talk has got the pompous title of Creating New Scientific Knowledge, but the subtitle is probably more appropriate, which is the thing in brackets underneath it, A Random Walk Through Physics to a Nobel Prize, which is really what happened to me. So I will try to use my example of my own random walk to the Nobel Prize as an example of how new knowledge can be created, albeit accidentally. Now, in 2016, 3 of us got the Nobel Prize, and I happened to be in Finland on sabbatical, and I was in an underground car park in Espoo in Finland, waiting to go up to the mall for sushi and beer. And my cell phone went off in my jeans pocket, and I managed to get it out and answered, and this Swedish accent came over the phone, mumble, 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 Nobel Prize. And I just sort of stood there in astonishment, trying to think of something to say. After about 30 seconds, the only thing that came out of my mouth was a mild expletive, because I really couldn't think of anything to say. I was so astounded. Now, the prize was actually given for, I guess you would call it, the application of topology to physics. And the 3 characters involved are, in the middle is David Fowlis, to the left is myself, and to the right is Duncan Haldane. And when I first heard of the Nobel Prize, and I found out how the prize money was split up, I got a bit, how should I say, annoyed, because simple arithmetic said that 3 people, you should get third each. However, it turned out that the prize actually awarded for 2 separate but related pieces of work, and there were 2 people involved in each piece of work. So the prize money was split, obviously, 4 ways, quarter each. But this violated one of the rules of the Nobel Prize, which is that there's a maximum of 3 people. However, the problem was neatly solved because 2 of the 4 people were the same person. And that person was the character in the middle there, David Fowlis. So the split became very, very fair, that it was a quarter each, and since Fowlis was 2 people, he got a half. So in any event, let me continue to try to tell you a bit give you this example of how progress in scientific knowledge can be made. Now, the problem is that what is new knowledge? And basically, my view of it is that it's simply a new discovery. And the problem is that a new discovery is really comprehensible at the beginning only to a few experts. And in order to be widely accepted, it has to be rewritten in different forms and applied to more familiar situations. Now, I like to think of the scientific effort as being of 2 distinct but related parts. And the first part is sort of a knowledge base, which can be regarded as the theoretical basis of various scientific fields, such as chemistry, physics, whatever. And the second part is the engineering aspects, which are just the applications of that knowledge. Now, this separation is not so easy to understand in many fields, but in my own field of theoretical physics, it's very easy to understand, because the theory is, the mathematical theory, and the Practical applications are everyday familiar devices such as your cell phones, which you all know, televisions, automobiles, etc., etc. Now, of course, these devices very likely wouldn't exist without the associated theoretical knowledge. For example, it's said that the automobile was invented by people with no knowledge of the underlying physics, and you could ask, why do I insist the underlying physical theory of engines was necessary? Now, maybe the inventors and builders didn't know about the underlying theory. As interestingly, in my case, the practical device appeared before the theoretical understanding. For example, the theory of thermodynamics, which I'm sure you all know and hate, grew from the desire to better understand and to make more efficient the steam engine. And this was an early example of the intimate relation between scientific theory, thermodynamics, and the applications, heat or steam engines. And after all, steam engines were at one point used in transportation and powering machines in industry. I've even got a picture of an early steam engine, which I had to show you because it's very pretty. Of course, the physicist's idea of the picture of a steam engine is a bit simpler. Basically, all it does is it extracts some heat from a hot reservoir, the boiler, it feeds this into some engine which extracts a certain amount of mechanical work, and then exhausts the cooler operating substance, which in this case is steam, water vapor, to the cold reservoir, otherwise known as the atmosphere. Now, internal combustion engines in your car, they operate on a similar cycle called the Otto cycle. For example, here's a picture of the Otto cycle, which you've probably all seen. That's, if you like, from the leg from 2 to 3 is the ignition. When the pistons are top dead center, the spark plug fires, the petrol or the gasoline air mixture explodes, and the pressure increases dramatically. Then 3 to 4 is the exhaust cycle. 4 to 1 is when the exhaust valve opens and the pressure drops dramatically, but the volume doesn't change. And 1 to 2 is the compression cycle, and so on. So this goes round and round and makes your car run. Of course, the real internal combustion engine is slightly more complicated than this diagram. Now, another example of new knowledge which we all know and love, or all know and hate, is James Clerk Maxwell's work, who's a Scottish scientist who wrote down the equations encapsulating the laws of electromagnetism back in the 19th century. Now, these laws, as we all know, work perfectly well today, and basically there's no fault, there's no difficulty with them, except, of course, the minor problem of solving his equations, which are not too easy, especially with boundary conditions. For those students who have been plagued with various problems from electrodynamics and electrostatics, I'm sure you remember that the main difficulties are in the boundary conditions. Then the propagation of one of the main discoveries was the propagation of electromagnetic waves through empty space. And these waves carry energy, which explains why we can see each other, why we can see the sun, the moon, and so on and so forth. Now, this was, at the time, was very new because in those days, people thought that waves of any type needed some sort of medium to propagate. And so the general thought was that space should be filled with some medium, which they called the ether. Eventually, of course, an experiment was done, was a Michelson Morley, who demonstrated that the ether didn't exist. And so people had to admit that actually Maxwell was right and that the electromagnetic waves do propagate through free space. Of course, more interestingly, these electromagnetic waves explain why we can see the world in color. And this is because the normal human eye, or even the abnormal human eye, absorbs energy carried by the light rays, and the energy excites some receptor in the eye, which sends a chemical signal to the brain, etc., etc. Now, these examples are, of course, very old and well known, but do illustrate my point that any scientific discovery which goes against accepted wisdom does face some opposition from the proponents of the old incorrect wisdom. Perhaps even better known is the case of Albert Einstein, who wrote down his theory of relativity. Now, initially, this was not understood by very many people, but of course has since been demonstrated to be correct in all respects. That's including this general theory of relativity, where gravity waves were originally contained, and these gravity waves are only fairly recently discovered to actually appear. For instance, the LIGO observation. Oh, here's a picture of Einstein, which I stole from some old book. Now, another example of scientific discovery I take from closer to home, because here is a picture of my father, he's the tall one, and myself, the small one, at an early age. Now, actually, my father's the person responsible for turning me on to science, because he was a physiologist. He started life as a physiologist, I should say, and he came from Germany, had to leave because he had a problem with Hitler, who allowed him to work in a hospital in Berlin, but not to be paid. And so he decided that things weren't too good for somebody coming from a Jewish family, so he moved to the UK. Okay, now, here's now in my own case, I was a sort of rather, I could say, a failed high-energy physicist, because I was, my career went that I did my graduate studies at Oxford University in high-energy physics, and then had a postdoc position in Italy, in Torino. Of course, the reason why I was there was not so much for the physics, but more for the proximity to the Alps, because my main interest wasn't so much physics, but more rock climbing and such other entertainments. Now, so I was basically a high-energy physicist doing all sorts of complicated calculations for very little return. I was working on something called the Veneziano model, which was the precursor to modern string theory. But, of course, what did I know? I didn't know that eventually string theory would be something very important. And anyway, it was all too complicated for me to understand. And so I was working on some elaborate calculations, and I was just about to finish the calculations, just about to start writing them up as an attempt to get them published, when the preprint arrived at my desk. I remember I'm talking about ancient history before the days of the internet and so on, so most of you can't conceive of communication by paper preprints sent through the mail. But it really was like that back in the old days. Now, so I was sitting there doing my calculations on my own in a small office in Birmingham when, and as I said, I was just about to write up these calculations for publication when the preprint arrived on my desk, doing exactly what I was trying to do. So I thought, okay, these things happen. And started the next calculation. And then exactly the same thing happened again. At which point, I threw my hands up in the air, said a few choice words, and started walking around the department asking every person I found, do you have a problem that maybe I could look at? The answer was consistently no, until I found myself in the office of one David Fowlers. Now, I had been warned by my colleagues that David was a very difficult person who, let's put it this way, didn't suffer fools gladly. Now, David was a sort of theoretical physics genius. You know, I would put him on this, maybe this opinion is wrong, but I would put him on the same level as people like Richard Feynman, Phil Anderson, any of the old physics heroes you can think of. Basically, Fowlers knew everything about everything and was able to think out of the box. And so after plucking up my courage to approach this person, I found myself in his office listening to him talking about various weird and wonderful concepts, things like superfluidity, superconductivity, melting of two-dimensional crystals, phase transitions in 2 dimensions, all subjects I had no idea about and had never really come across, mostly because as a high-energy physicist, I had decided that statistical mechanics was an unnecessary complication. In exactly the same way as I am these days very ignorant of quantum mechanics, unfortunately, because I basically have spent my life trying to avoid quantum mechanics as an unnecessary complication. Everybody can be wrong. Okay, now, so Fowlers and I listened to Fowlers standing there while he was writing on the board, and eventually, I realized I was really lost. I wasn't understanding a single word. And then, so in desperation, I thought, I've got to do something about this. This is ridiculous. I can't stand here for the next hour not understanding a word. So I plucked up my courage and decided that I'll look like a complete fool. But I said, I'm sorry, David, I'm a bit lost here. Could you please back off and could you tell me where your first equation on the board, where did that come from? He turned around and looked at me and said, didn't I tell you that? And I could honestly say, no, you didn't. And at which point he said, oh, and then proceeded to give me a very clear explanation. Now, At this point, I decided that should I happen to work with this person or have any further contact with him, which I thought was somewhat unlikely, and I couldn't understand what he was talking about, I would assume he'd done the same thing and had forgotten to tell me something important, and so I could ask these standard stupid questions. Now, fortunately, this attitude worked, and Fowler seemed to appreciate being asked stupid questions. Now, you have to remember that Fowler was a guy whose mind operated on a different level to the great majority of us. And so that basically compared to him, almost everybody else was, came over as a fool because they simply didn't understand so much. And for the students, I can assure you that approaching a man like this requires you requires a thick skin, let's say, because I remember he would, if you asked something stupid, he would explain very slowly, very carefully where you'd gone wrong. And the end result is that, I used to feel like a complete idiot because I shouldn't have to be treated like a small child, but it worked. Anyway, so he was discussing all sorts of weird and wonderful concepts, things like, as I said, phase transitions in 2 dimensions, superfluidity in 2 dimensions, superconductivity, and he proposed some ideas which were completely contrary to standard wisdom. I mean, for example, he was talking about things called topological excitations. Now, I wouldn't know, at the time, I wouldn't have known a piece of topology if it sat up and balked. So I was a little bit, confused by what he was talking about. But eventually, when I got back to my own office and I sat there staring out the window trying to process what I'd heard, some of those ideas started making sense. And so I started working on it, and eventually took my calculations back to him and said, well, I've done this, what do you think? And he looked at it, said, hum, ha, etc. And then, okay, we should refine it a bit and we'll write it up for publication. So we did. And this paper is actually the work for which we got half the Nobel Prize. So this was the most amazing experience because I started thinking all physics is like this, where you're working on these wonderful ideas where you could do actual calculations and get actual numbers out. And, I just expected all physics to be like this. So later, of course, when I was left to my own devices, I tried to repeat what Thales and I had done, and failed miserably every time. I'm still trying and still failing. And so it turned out this work was fairly important. I mean, the important point is that it started off as an interesting theoretical problem. We had no idea at the time that we were doing something important, or at least I had no idea. I mean, it could be that Thales actually knew we were doing something important, but he didn't tell me. One of the pieces of evidence we had staring us in the face about two-dimensional phase transitions was this piece of experimental data. It was an experiment done by these three characters, Chester, Yang, and Stevens, and it was published in Phys Rev Letters. And we had this result earlier as a preprint, and this was the central piece of evidence that a phase transition did exist in the systems that we were interested in. Standard theory, standard wisdom said that could be no transition, because standard theory said that our low-temperature ordered phase had to have long-range order. This was the law laid down by Lev Landau. However, it was also a rigorous theorem which said that two-dimensional systems of this nature had no long-range order at any finite temperature, from which the natural conclusion is there's no phase transition because there was no possibility of long-range order. However, this experiment was staring us in the face, where it was basically experiment consisted of absorbing helium, thin film of helium on the surface of a resonant crystal, and then measuring the reduction in resonant frequency due to the extra increase in mass due to the absorbed thin film. And if all the fluid was stuck to the crystal, then you'd expect that the reduction in the resonant frequency would follow the straight line. The experimental data for low coverages did follow the expected straight line, as you can see, but then suddenly deviated, and there was a big discrepancy between the expected result and the experimental result. And so this was indicating that, of course, there's a phase transition here where some of the fluid decoupled from the resonant crystal, and therefore the easiest interpretation was this was superfluid, and this system had undergone a phase transition. Now, okay, this was, of course, not, these ideas were not accepted by the physics community, and it wasn't really accepted until the definitive experiment was done by Bishop and Reppy at Cornell in the late 70s. You see, what they measured was the superfluid density, which is the mass per unit area, again, just below the onset temperature, as a function of the onset temperature. And the theoretical prediction was that solid straight line. Then, if you take a series of experimental data and plot it the same way, the experimental results are all scattered around the straight line. And to me, being biased, this looks like confirmation of the theory. Okay, so let me just finish. You can do the same thing for melting in 2 dimensions. And, all right, so the work, let me just conclude, the work for which we got our share of the Physics Nobel Prize in 2016 was a theoretical explanation of the phenomenon of superfluidity, superconductivity, and the melting of a crystal in 2 dimensions, or alternatively flatland. And to just prove that I was actually there, there's a picture of my wife and myself with the Swedish royal family. I have to show such a picture because it's this fairly definitive proof that I actually was there. And, okay, so let me conclude by saying that new knowledge in science can occur. And in my case, I would say that it involved about 95% dumb luck and 5% smarts. The luck is being in the right place at the right time and doing the right problem. And the remaining 5% smarts is no more than the ability to do the necessary arithmetic involved. So, in conclusion, let me say to the students here, you too could be lucky. Remember, it's mostly luck to end up with a major prize. It's not just being smarter than anybody else. It's luck. It's being in the right place at the right time and doing the right problem. And how you arrange that is beyond me. I was lucky, and all the necessary criteria were fulfilled, and I happened to be sufficiently, if you like, smart to be able to do the necessary arithmetic. That's all. And so, thank you very much.